remember if mine was May 4th or May 5th?
Yeah.
It's okay. I know it's on Tuesday. We're on Tuesday. So physics is Monday. We're on Tuesday. That's what I know for.
That's what it is. Because I have to probably take the makeup physics exam.
Why?
That weekend is our end of the year competitions for years.
So you'll be cord. So you'll be in. Yeah.
I'm probably gonna have to make up everything.
Yeah, it's not a big deal. It's just a lot of paperwork. And if you know that now, I would go talk to Mr. McNally now so he can just schedule you as such.
Yeah.
All right. So here is that first handout right here with the F. So this worksheet, this chart, this table is like the most summarizing summary that you could really have. It is super informative. So if this is something you're struggling with, or you don't like that table I gave you with the F prime, F double prime, the table maybe confuses you, this is something I would maybe take a picture of or, keep with me if it's something that you are still struggling to understand. Because like I said, this is going to give you all of those key critical points kind of nicely put together. Okay. And then the page that was after that was another one of my own created CUDA assignments because I think that seeing graphs and interpreting graphs is very important for us. So for number 1, here's all your key pieces of information. All right, number 2. All you had to do in number 2 is sketch that graph. So if the first derivative does not exist at -2, then there's typically something happening on the original at that same -2. This graph is decreasing and negative, so that tells me that my original graph is concave down and decreasing as well. Increasing and negative tells me that my other graph is concave up but still decreasing. So the negativity tells me the decreasing, and then the increasing or decreasing gives me my concavity. Okay, number 3, you also just had to sketch that graph. So in order to sketch it accurately, I'm looking at, okay, this is positive until 0. So that tells me I'm increasing until 0. From 0 to 4, it's negative. That tells me I'm decreasing on both of those intervals. And then again, at f prime of 2, it does not exist. So that tells me that the function is not differentiable at 2. So you could have had that vertical asymptote. You could have drawn in a jump discontinuity, but you need to do something along those lines. And then continuing on, it's positive from 4 to infinity, so it told me it was increasing. Remember that zeros of the derivatives are extremas of the original as long as we have a sign change. And we have a sign change at 0 and 4, thus making 0 and 4 extremas of the original. So you wanted to kind of put or enunciate those key points. And then number 4 was kind of like the combination of calculus and physics sort of together. We're talking about particle motion. So you had to give me velocity and acceleration. And then we talked about where does it change directions, what direction is it going where. And then the all-important speeding up and slowing down. So again, it is speeding up if the signs are the same. So both graphs are positive until that 8/3. So from 0 to 8/3, they're both positive. Therefore, we have speeding up. From 8/3 until about 5.13 or 16/3, we are opposing signs. Therefore, it is slowing down. And then from 16/3 on, both graphs are negative. Therefore, we are speeding up again. So speeding up and slowing down directly relates to the signs of velocity and acceleration. Okay, I'm going to send you the answers to the other 2 handouts because I don't have them printed. So I'll be sending those during the day today. And if you have questions, you can come back period 2 or 3, whatever the one we're calling the end of the day, and ask, check at the beginning and ask any questions you might have. So that being said, I'd like to start 4.4 with you. I know we're not going to get through all of 4.4 because of the 2-hour delay. So we're going to take out those 4.4 notes. With the 2-hour delay, we're not going to do the bell ringer. So you guys in person, I actually didn't even print it off for. We're going to start with the word optimize. And we're going to talk about what does that word mean. So how effective is to basically solve a problem that requires a function to be maximized or minimized. Optimization problems are directly related to real-world applications of business, economy, phenomena that happen, which you'll see in some of these examples as well. A lot of things you use in your everyday life have been optimized by a mathematician or engineer for a company. So the size of a pop can is something that we've investigated in the past because we talk about the use of aluminum, especially this year. Canned companies are really looking to optimize because aluminum is at such a low. Companies that make boxes, like Amazon, they look to maximize or minimize the amount of surface area of cardboard, etc. So those are the types of problems we're going to look at. So historically, optimization problems were among the earliest applications of what we call differential calculus. Anybody thinking about going into engineering or mathematics will have to take a class in college called differential calculus. We always just called it diff-EQ. You're going to use like partial derivatives and a lot of the things we're going to talk about in calc today at a much deeper level. So where do we use this? This is actually one of, like I said, the most commonly applied uses of calculus. It can be used for profit, cost, time, voltage, size, distance, strength. So the word optimize means to minimize or maximize. So your definition for optimize is to minimize or maximize. Again, your word or definition is to minimize or maximize. So I've given you the directions. We're going to follow a 6-step process for these problems. At first I number them, but then I'll stop numbering them just because it becomes something you don't need to see or do. But the application of the numbering is helpful in the beginning because it allows you to follow a pattern and kind of make sure you're doing each of the steps you need to do to get to that finalized answer. Okay, so find two numbers whose sum is 20 and whose product is as large as possible. So what we do, this is a problem. If we follow the directions, we're going to read it. We're going to look at what we know, what we want to know, and what we understand. So I know I need two numbers. I need their sum to be 20 and their product to be large. So a large product, that's what we are maximizing. So we'll call X number 1, and we'll call Y number 2. There's not really a picture to draw for this, so we'll skip step 2. 3, introducing our notation. So we have X plus Y equals 20. So that helps with the first part, two numbers whose sum is 20, and then whose product is as large as possible. So we'll say P equals X times 20. So we obviously don't want to do implicit differentiation. So what we're going to do is substitute. So I want you to substitute in, guys, I want the phones and the laptops put away. Unless you're taking my notes on a laptop, which I doubt you are, put it away. If you're playing on your phone, put it away. This is a calculus lesson. We are starting a new unit. I shouldn't have to tell that to AP students. It wasn't just you. I've watched other kids on their phone this morning. Okay, so we have X equals 20 minus Y. So what we're going to do is replace one variable with the other. We're going to substitute in one for the other. So we're going to replace X with 20 minus Y. Therefore, that puts us in terms of one variable. You could also have done the opposite. So maybe you like to have everything in terms of X. So maybe instead of solving for X, you solved for Y. That's fine too. You could have had Y equals 20 minus X. And then you replace Y with 20 minus X. So both will work. You just pick a variable and substitute it in. The process and the numbers are going to be identical. What's going to happen is your variables are just going to switch what order you solve for them. So we have P equals X times 20 minus X. Or you had P equals Y times 20 minus Y. Doesn't matter. So that gives P equals 20x minus x squared. So that represents the product. But if you want to maximize a product, how did we find the maxes of a function? Well, the max is good. Chase, what do you think? Yeah. Perfect. So we're going to find the derivative of that product. And then to maximize it, we're going to set it equal to 0. Because the zeros of the derivatives represent the extremas of the original. So we get 20 minus 2x. And then we set that equal to 0 and solve. Then we get x equals 10. And then we solve for y by plugging 10 in for x. And we get y equals 10. Should it make sense that the two numbers with a large area are a square? Usually when you're trying to maximize area, the most maximized areas are typically squares. Most maximized areas occur at squares, an even length and width. Now, not all squares are going to work for every problem. Okay? So, a problem I'm sure you've seen before in Algebra 2. I feel like I actually use almost an identical example in my Algebra 2 classes. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So here's my field. Here's my river, or my side that needs no fencing. So I'm drawing my picture. And I'm going to label my picture. So if we're talking about dimensions of a field, we're typically talking about length and width. I try not to use L and W's because if you use an L, you got to make it cursive. So I'm just going to do X and Y, but if you did L and W, that's fine. But again, I just try to avoid them because they end up becoming cursive. So we'll say that X is the width and Y is my length. So that 2,400 feet, what does that represent? Well, that represents the perimeter where we are using fence. So we're using fence along these three sides here. So what that means is that 2,400 feet of fencing is equal to 2y plus x. So perimeter equals the length and the widths. Now, since I only have one width, it's 1x. We are trying to maximize area. So I need to get my formula for area. So area equals length times width, or x times y. Once again, you guys don't want to do implicit differentiation. So I'm going to substitute one formula into the other to eliminate the need to use implicit differentiation. The easiest variable to solve for is x because it doesn't require me to divide by any values. So I'm going to come over and say, okay, x is equal to 2,400 minus 2y, thus making area equal to 2,400 minus 2y times y. So now area is in terms of one variable. So now I can distribute, derive, and find my zeros. Because the zeros of the area will be the maximums, or the zeros of the derivative will give me the maximums of my original area. So A is equal to 2,400y minus 2y squared. A prime is 2,400 minus 4y. So you set that equal to 0. Solve for y. you get 600, because 24 divided by 4 is 6. So 2400 divided by 4 is 600. So it asks for the dimensions though. So we're not done. We have to find x as well. And we're back to incorporating units. So it's 600 feet. And x would be 2,400 minus 2 times 600, or 1,200 feet. So the dimensions of the field with the largest area using all the perimeter fencing is 1,200 by 600. So, like I said, the steps to doing these are read the problem, draw a picture, label your picture, and write your equations. So we have a sheet of cardboard, 3 feet by 4 feet. So that would be 3 feet by 4 feet. It's being made into a box by cutting equal sized squares. So what that means is each of these orange corners, as I drew them in, are all identical. So the length of one is the same as the length of the other. So if I labeled each of them, they're all x's. So we cut out equal size squares from each corner, and then you fold up the 4 edges, and you would seam the corners together, and that would give you an open top cardboard box. What dimensions of this box will hold the largest volume? So I am trying to, or my goal is max volume. So in order to do that, I need to talk about what I have and how I can utilize that. So this length here is going to be 4 minus 2x. So all of the sides are going to incorporate that x in some way. So volume equals length times width times height. So we need to identify what is the length, width, and height. So if you imagine those edges being folded up, the height is the height of each of the corners being cut out. So my height is x. The length is the entire sheet of cardboard, so let's say 4, but we're cutting out these corners. So this is x and this is x. So the length is 4 minus 2x, because you're taking x away from each of those edges. Just like my width is going to be 3 minus 2x. So my volume is 4 minus 2x, 3 minus 2x, times x. What's nice about this problem is once I do the substituting, I have one variable for volume. Now, nobody wants to do a product rule, so you're better off distributing each of these in. So I would say 4 minus 2x equals 3x minus 2x squared. And then I would FOIL, so you have 12x minus 6x squared minus 8x squared plus 4x cubed. Now, if you wanted to take the derivative at this point without combining the 6 and the 8, that would be fine. So your derivative is 12 minus, and again, I know that 6 and 8, and again, just because I'm running out of room, that would turn to 14 x squared. So that would give me negative 28x plus 12x squared. So what makes volume a little different than the area and perimeters is that this is now a squared function. So I'm going to potentially get 2 roots, which means I need to figure out which one is going to give me the smallest volume and which one is going to give me the largest volume. So you could factor it like this. You could rearrange your terms so that it was 12x squared minus 28x plus 12. So when you guys come back at the end of the day, we will pick back up and finish this problem. So I'm just going to kind of pause for now, and we will finish and pick up at the end of the day.